number 1 is in on your screen. Okay, so what we are going to do today, the in-text question of chemical kinetics. First question is, for the reaction R to P, concentration of a reactant changes from 0.03 molar 0.02 molar in 25 minutes. Calculate the average rate of reaction using units of time, both in minutes and seconds. See, how do we proceed? You know, the rate of reaction. It is equal to minus delta R over delta T. That is minus final concentration, means difference of final to initial concentration over the T2 minus T, means time taken, can be written as decrease in concentration of reactant divided by time taken. This negative sign only indicates the decrease. See, minus, what is the concentration? Final concentration is 0.02 and initial concentration is 0.03 divided by 25. So it is equal to minus 0.01 molar divided by 25 minutes. Means it is equal to 0.01 over 25, or we can write it as minus plus, so 100 over 25 into 10 raised power minus 4, right? Because it is 0.01, so it is 1 into 10 raised power minus 2, and 100 upon, if it is multiplied by 100, so it is 10 raised to power minus 4. So it is 4 into 10 raised to power minus 4 molar, is mole per liter per minute. It is the answer in minutes, molar per minute. Okay, now in seconds. So to calculate the answer in seconds, what we do? Just we write the rate of reaction equal to, now time as it is 25 minutes, so it is equal to 25 into 60 seconds, right? So it is equal to again minus 0.03 minus 0.04 molar divided by 25 into 60 seconds. What is the value? 0.01 molar divided by 25 6 ja 150, 1500 second. Yes, sorry, 0.02. Oh, sorry, 0.02. Okay, final is 0.02 and initial is 0.03. Okay, sorry. It is 0.02 minus 0.03. Thank you. So it is equal to, let us take it as 1000 over 1500 into 10 raised to power minus 5 mole per liter per second. It is 10 over 15 means 2 over 3, that is 0.66, or we can write 7 into 10 raised per minus 5 molar per second, or we can write it as 6.7 into 10 raised per minus 6 mole per liter per second. Okay, so this is the rate of reaction in terms of seconds, and this is the rate of reaction in terms of minutes. 4 into 10 raised per minus 4 mole per liter per minute. Right? Question number 1. Just check the answer. Is it okay? Next, in the reaction 2A, two products, concentration of A decreases from 0.5 mole per liter to 0.4 mole per liter in 10 minutes. So calculate the rate during this interval. Okay, so reaction is 2A, two products, and we have to calculate the rate during this interval. So rate of reaction. So obviously it is average rate of reaction, okay? Because the interval is given in 10 minutes. So average rate of reaction is equal to, again same, minus A2 minus A1, final minus initial, divided by time taken. Minus 0.4 is in final concentration, 0.5 is initial concentration, and concentration is given in mole per liter, divided by time. So time is 10 minutes. So it is equal to 0.1 mole per liter divided by 10 minutes. So in minutes, value comes out to be 0.01 mole per liter per minute. This is the average rate of reaction in terms of minutes. Now in seconds. Yes. Okay, it is 2A products. Okay. It is 1 by 2 then, because it is 2A to give products. So it is again 1 by 2, 1 by 2. So 1 by 2 into 0.01, it is equal to 0.005 mole per liter per minute, or we can write it as 5.0 into 10 raised to power minus 3 mole per liter per minute. You can calculate in seconds as well. So to calculate the same rate in seconds, again same relation, half 0.4 minus 0.5 mole per liter divided by 10 into 60 seconds. It is equal to half into 0.1 divided by 600, is it is equal to 0.1 upon 1200, means 1 upon 1200, it is 8.33 into 10 raised to power minus 4 mole per liter per second. Minus 5. Okay, yes, it is 10 raised to power minus 5 mole per liter per second. Next, for a reaction A plus B to product, the rate law is given by R equal to K A raised to power half B raised to power 2. So what is the order of reaction? So you know what is order of reaction? The sum of the powers to which concentration terms are raised. The order of the reaction is sum of the powers to which concentration terms are raised. Means it is half plus 2. So it is equal to 1 plus 4 means it is 5 by 2, or we can write it as 2.5. This is the overall order of reaction. It is half order with respect to A and second order with respect to B. And overall order of reaction is sum of these powers. Sum of the powers to which these concentration terms are raised. Okay. Next question. The conversion of molecules X to Y follows second order kinetics. If concentration of X it is increased to 3 times, then how will it affect the rate of formation of Y? Okay. See, the rate of reaction follows second order kinetics. That means conversion of X to Y is the rate of formation of Y. Rate of formation of Y is rate constant into X raised to power 2, because it follows second order kinetics. So X raised to power 2. If concentration of X is increased to 3 times, see, let us take it as R1, that is initial rate. Now, when concentration of X is increased to 3 times, then R2 equal to K 3x raised to power 2, because concentration of X is now 3 times. Initially, if it is X, then finally, when it is increased, it becomes 3x. So it is equal to 9k into x raised to power 2, means it is equal to 9r1. That means the rate of formation of Y, rate of formation of Y is increased to 9 times. When concentration of X is increased to 3 times, then rate of formation of Y is increased to 9 times. Next question. A first order reaction has a rate constant. See, a rate constant is given to you. Rate constant is 1.15 into 10 raised to power minus 3 per second. How long will 5 gram of this reactant, that means initial concentration is 5 gram and final concentration is 3 gram, and reaction is of first order, rate constant is given. So how long will 5 gram of this reactant take to reduce to 3 gram? Okay, so now time for first order kinetics. For first order kinetics, time is equal to (2.303) over k log of r naught by rt. This is the formula to calculate time for the first order kinetics. It is integrated rate equation. It is equal to 2.303 divided by 1.15 into 10 raised to power minus 3 log of 5 over 3. It is equal to 2.303 10 raised to power minus 3. If it is the numerator, then it is multiplied, so it becomes 2303 divided by 1.15 into log 5 minus log 3. That is 2303 divided by 1.15 into 0.699 minus 0.477. Log 5 is 0.699 and log 3 is 0.477. So it is equal to 2303 by 1.15 into 0.233, right? So it becomes 303 into 0.233 divided by 1.15. So it is 466.6 seconds. Time is in seconds. Or to calculate in minutes, just divide it by 60. It becomes 7.78 minutes. Okay, so that is question number 4.5 in text question 4.5. 4.6 time required to decompose SO2 Cl2 to half of its initial amount is 60 minutes. It is 60 minutes. Okay. So now if the decomposition is again first order reaction, to calculate the rate constant of the reaction. The time required to decompose to half of its initial amount that is given to us. Means half life is given to us. Half life is 60 minutes. So if half life is 60 minutes and reaction is first order, so for first order kinetics, what is the relation between half life and rate constant? So half life is equal to 0.693 over k. The relation. So k equal to 0.693 divided by t half. That is 0.693. It is divided by 60. So it comes out to be 0.693 divided by 60. It is 0.01155 per minute, or we can write it as 1.155 into 10 raised to power minus 2 per minute. Okay. Next question. What will be the effect of temperature on the rate constant? Keep in mind, there is a rough estimate as an approximation for every 10 degrees Celsius rise in temperature, rate constant is almost doubled or sometimes tripled. See, for every 10 degrees Celsius rise in temperature, rate constant is almost doubled or sometimes tripled. Okay, and for an exact calculation, for exact dependence of temperature on rate constant, Arrhenius equation is used. That is K equal to A e raised to power minus A by RT. Okay. Where A is frequency factor or pre-exponential factor. EA is activation energy. R is gas constant, and T is temperature in Kelvin. So we can say that on increasing temperature, rate constant is increased. Simply write this thing. Okay. Now rate of the chemical reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. Means initial temperature is given to you. It is 298 Kelvin and final temperature is 10 Kelvin more. That is 308 Kelvin. Right? Now rate of reaction, that means rate constant, doubles. That means K2 by K1. K2 is the rate constant at temperature T2 and K1 is the rate constant at temperature T1. This is called temperature coefficient and its value is 2. Yeah, rate of chemical reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. From this statement we extract these things. T1, that is given 298 and increase of 10 Kelvin. So T2 is 308 and when this temperature is increased, the rate of chemical reaction doubles. That means K2 by K1 equal to 2. Now according to extended form of Arrhenius equation, according to extended form of Arrhenius equation, now K2 over K1 is equal to EA upon 2.303 R T2 minus T1 divided by T1 into T2. This is the relation. And what is log 2? Because we have to calculate activation energy. EA we have to calculate. So from here, K2 by K1 we have, T1, T2 we have. What is left? R. So value of R is 8.314 joule per Kelvin per mole. R is 8.314 joule per Kelvin per mole. Just put the values. Log K2 by K1 is 2. Log 2 equal to EA divided by 2.303 into 8.314 T2 minus T1, that is 10 only, but just write whole value is up to you. Just write 10 into 298. Okay, T1 into T2, 298 into 308. Okay, now log 2. What is the value of log 2? 0.3010 EA upon 2.303 into 8.314 to 10 divided by 298 into 308. So EA equal to 0.3010 into 2.303, 8.314 into 298 into 308 divided by 10. So activation energy equal to, just multiply them, 301.301 into 0.303 into 8.314 into 98 into 308. It is 528978. 528978 joule per mole. So activation energy equal to, okay, divided by 10. So it is joule per mole. So it is equal to 52 kilojoule per mole. Means it is round about 2.9 kilojoule per mole. Yes, beta. Any doubt up to this? So last question, that is activation energy for the reaction 2HI gas to give H2 gas plus I2 gas is 209.5 kilojoule per mole. His activation energy for this particular reaction is given to us. It is 209.5 kilojoule per mole. Just convert into joule. So it is 209.500 joule per mole. This is activation energy in joule per mole. at 298 Kelvin, temperature is given to us 581 Kelvin. So we have to calculate the fraction of molecules of the reactants having energy equal to or greater than activation energy. So you know that fraction of molecules of reactants having energy equal to or greater than EA equal to, take it as X and is equal to E raised to power minus EA by RT. So we have to calculate this X. Activation energy we have, temperature we have, R we know. So all the values we know. So just take R 8.314 joule per Kelvin per mole. So X we have to calculate, right? X is E raised to power minus EA by RT. So taking natural log on both sides, because base E is of natural log. Taking natural log on both sides, natural log of X is equal to minus EA upon RT. So natural log convert into common log, 2.303 into log X equal to EA upon 0.30, sorry, EA upon RT, negative sign. So log of X equal to minus EA divided by 2.303 into RT, and values, just put the values. EA is, what is EA? 209500, 209500 joule per mole divided by 2.303 into 8.314 joule per Kelvin per mole into, what was the temperature? 581 Kelvin. 581 Kelvin. So quantity becomes dimensionless. So log of X is equal to 209500 divided by 2.303 divided by 8.314 divided by 581. It becomes minus 18.832, minus 18.832. Now make the mantissa positive. Minus 18 minus 0.832 plus 1 minus 1 means it becomes minus 19 plus 1 minus 0.832, 0.168 becomes 19 bar 0.168. X is equal to anti-log of 19 bar 0.168, that is 10 raised to power minus 19 into anti-log of 0.168. It is 1.47 into 10 raised to power minus 19. So this is the fraction of molecules having energy equal to or greater than EA. Fraction of molecules having energy equal to or greater than EA. That's all. These are all in text questions of chemical kinetics. Yes, beta. Any doubt? Okay, that's all. Yes, beta. So that's all about today's lecture. These are the in-text questions of chemical kinetics. See, we will do all the NCERT questions, NCERT in-text questions, examples, NEET questions, AE questions of each and every chapter of class 11 and 12. And they are all, this is all free of cost. So support this free education drive, support my channel, share with your friends, share in the groups, in the community where it will be gained, or it will involve the large mass of students, so that all will be benefited and my channel will grow. This is the only my aim, that all will be benefited from this free education drive. See, coaching institutes will charge around 1 lakh if they cover NCERT concept along with NEET and JEE. But in my channel, it is all free of cost. Just enjoy learning and ask others to join, that all will be benefited. Thank you so much to be with me and supporting my channel.